Hi, welcome to Lesson 16b, Increasing and Decreasing Functions. The goal of today's lesson is to use knowledge of gradients of tangents to determine where curves increase and decrease. So first of all, we have to take a look at a couple, some forms of intervals so we can kind of get our teeth wet or sink our teeth into the topic here. Whet our appetites, I guess. So if we have some algebraic form of intervals, we could say something like x is greater than or equal to 5. And then to compare that, we've got the geometric form, and we can draw on a number line what that looks like. So suppose this is 5. Then if it's greater than or equal to 5, that means that the value of 5 is included. So we have a closed circle there. And then we'll just draw, as I reload, the interval going to the right because it's greater than, and because it's equal to, that means that it's going to have a closed circle. If we have something like x just greater than some value, say let's say -3, just to mix things up a little bit. If this is -3, for example, I know these aren't related at all, these two number lines. So there's -3, and if it's just greater than and it does not equal to, then we have an open circle, because it gets as close to -3 as possible without actually being equal to -3, and then it's greater than, so the arrow goes to the right. We could do the same sort of thing. Suppose now we start with the number line and we say that something is, let's say it is like this, and coming to the left, and this number is I don't know, 5/8, for example. Then that means, what would that mean? That means that x, okay, the open circle is 5/8, arrow pointing to the left, that it's less than 5/8. Do the same sort of idea here. Now the number line, let's say this is the number, I don't know, -7.5, and it's a closed dot, and the arrow is moving to the left. How would you write that algebraically? Then that would be x less than or equal to -7.5. Okay, and suppose then that we have a closed circle here, maybe an open circle here. Let's say this is -1 and this is 4, and the values are in between. Then we would say that x, or -1, is less than or equal to x, which means x is greater than or equal to -1. So, sorry about that, is to the right of -1, and less than 4, meaning that x is less than 4, or 4 is higher than x, but not equal to, so it's in between these two boundaries here. And then of course we could have variations of those. We could say negative, actually it doesn't even have to be negative, let's say 0 less than or equal to x less than or equal to 6. So then we'd have 0, we have 6, and because less than or equal to, then that means that there's a closed dot on both of these endpoints, and the value of x is somewhere in between there. So 0 is less than or equal to x, which means then that x has to be greater than 0 or possibly equal to it, and then the values of x are also less than or equal to 6. So it could be equal to 6 or less than. So that just means that x is between those two values. Okay, so that's just showing us about intervals that we've probably discussed in the past. Okay, so now that we looked at algebraic and geometric forms of intervals, suppose we're looking at some function and we want to look at some interval on the function, and this interval is s. And we know that the function is defined for all values of x in this interval s. So then what we can say is, so here's the interval, we can say that f of x is increasing on s when if f of a is less than or equal to f of b, meaning the y value that's given when f of x is evaluated at x equals a is less than the y value of the function when the function is evaluated at x equals b. Of course, when a is less than b. Okay, so we're just saying we're moving from left to right along the curve. So a is smaller than b. So we're moving from left to right. We see that f of a, the y value of the function when evaluated at a, is less than f of b, so the function when it is evaluated at x equals b. So that would, of course, mean that the function is going to some degree like this. So there's a, here's the x value of b, here's the f of a, so that's the y value, and we see that that y value is less than the y value of f of b, okay, when x equals b. So that just shows that the curve is increasing there. We can then turn this around and say that f of x is decreasing when f of a is greater than f of b, again when a is less than b. So we're still moving from left to right, and so if a is greater than b as we move from left to right, that would mean that the curve is something like this. So here's the x value of a, there's the y value of the function when when the function is evaluated at x equals a, and here is the x value of b, and we see that the y value of this function when it's evaluated at x equals b is less than f of a. So that is showing us that, of course, the function is decreasing, because if the y value to the left of this y value is higher, then that means that the function must be decreasing. If on some sort of interval the function is only increasing, then that means that it's called monotone increasing. If it's decreasing, it is called monotone decreasing. The textbook also uses the word strictly, strictly increasing or strictly decreasing, because they say that if, let's go back up here to the increasing, so if f of a is less than f of b, then they're saying it's strictly increasing, whereas they say from f of a greater or less than or equal to f of b that it's increasing. Now in my books, I don't like this equal to part, because if it's equal to, then that means that they're the same y value, which means that there would be a horizontal tangent, which means that it's not decreasing or increasing. Okay, so I prefer just to keep it as the just regular less than. But the textbook says strictly when it's less than, and just increasing when it's less than or greater or less than or equal to. And then they do the same thing for greater than or equal to. Okay, strictly if it's greater than, and just a normal decreasing if it's greater than or equal to. Okay, so that's a little bit about increasing and decreasing, and let's move along now to, if I were to look at this, what I was trying to diagram before is, here we see that this graph is increasing when f of a is less than f of b. Again, when x is less, or when x equals a is less than x equals b. Okay, we're always going from left to right along the curve. If, however, x equals a is here, and x equals b is around here perhaps, then we see that f of a is greater than f of b, therefore the curve must be decreasing, still as we go from left to right along the domain of the function. So we can take a look at functions and see how those things work just by looking at the graph. What we can do also, though, is if we know the derivative, well, the derivative, of course, as you will probably remember, is the gradient function, which is the rate of change, or the gradient of the tangent to the curve at any point along the curve. So if we know the gradient, we know the gradient function, we can calculate the gradient, and we can see if the tangent is either positive or negative anywhere along the curve. So as we draw tangents around the curve, we can see that here, to the left of this minimum point here, this turning point, where the gradient, or the gradient of the tangent is 0, that's a horizontal tangent. These tangents are negative because they're going down to the right. So that means that the curve is decreasing because it's got a negative gradient. And then over to the right of this turning point, the tangents are increasing, the gradients are positive, therefore the curve is increasing. And then we can do the same thing up here at this turning point, this local maximum. Here's the horizontal tangent, which means that the curve is neither increasing nor decreasing. And that's what I was talking about, the fact that if you say it's less than or equal to, well, if it's equal to right there, well, it's neither increasing nor decreasing. So you shouldn't really use equal to when you're talking about intervals of increase or decrease. It's better to use less than or greater than to show that the curve is increasing or decreasing. And so here we have another couple tangents. This tangent is positive, therefore the curve is increasing. It's got a positive gradient. And here on the other side of this horizontal tangent, this turning point, we see that the function is decreasing because the tangent is negative. Okay, so what we're going to do is I'm going to ask you to take a look at a few examples in the textbook. Take a look at example 8 on page 393. Then there's a few demos that you should look at on page 394. And then follow that up by looking at example 9 on page 394 and example 10 on page 395, which will show you a few more examples of increasing and decreasing functions. And then peruse exercises 1, 2, B, C, D, F, H, J, L, P, 3, 5, and 6, A, B, D on pages 396 to 397. We'll of course take a look at examples in class, and then you have time to work on this material. But until then, thanks for watching, and we'll see you in class.